So how do we quantify the importance of nodes? One obvious choice is to use degree. For example, for this node with 2 edges coming in, 3 edges going out, we say the total degree is 5, in degree is 2, out degree 3. Dunbar's number is used by sociologists as an estimate of the largest number of friends in a social network an average person can keep, usually quoted at around 150. But we also know that degree can be a misleading number to quantify node importance. For example, we may want to say that more important nodes pointing to you make you more important. And that is exactly what we did in lecture 3 with Google's ranking of web pages. Over there we say that construct a matrix G, which is a connectivity matrix H, plus 2 rank 1 matrices. You can view that matrix as a random walk-on graph model, for example, and then look at the dominant eigenvector, the eigenvector associated with the largest eigenvalue, in this case 1 of this matrix G. And then we rank web pages based on the entries of this vector. That's what we did with PageRank back then. And in general, the idea of eigenvector centrality. Centrality is just a fancier name to call importance of nodes. The eigenvector idea says that take the dominant eigenvector. The eigenvector associated with the largest eigenvalue of some meaningful matrix, such as the adjacency matrix A that we just defined. So why would you want to do that? One possible motivation comes from the following linear dynamic system interpretation. As in a homework problem, you see that we can often model many useful quantities in the dynamics of the functionality on a graph by looking at a vector x with 1 entry per node, evolved over discrete time indexed by t, as multiplying an initialization vector x at time 0, thus initialization, on the left by this incidence matrix A. At time t, it's been applied t times. Now, how do we understand this expression? We know that any given vector, we can decompose that, represent that as a weighted sum of the eigenvectors of this matrix A. Call those eigenvectors vi, and the corresponding eigenvalues scalars lambda I. And we can represent any initialization vector as the linear combination with weights ci of these eigenvectors. Now substitute this expression back into this evolution. We see the following expression: A multiplied on the left t times the summation of ci vi vectors. Again, ci are the weights to provide the linear combination among the vi's to give you this vector. Because this is a linear operation, we can pull the matrix multiplication inside the summation. Now, if you multiply the eigenvector, an eigenvector of this matrix on the left, then you just get lambda I vi, and you have done that t times. Therefore, it is just ci times lambda I raised to the power t times vi vector. In other words, we have expressed the time t vector x as a linear combination of the eigenvector of this matrix A here, where the weights are the ci times lambda eigenvalue lambda I times to the power t. So as time goes on, what would dominate this summation is really the one associated with lambda 1. So this becomes basically like C1 times lambda 1, the largest eigenvalue, times to the power t v1. In other words, x times t for large t is approximated by this v1, the dominant eigenvector, the one associated with the largest eigenvalue of matrix A. So we can take the largest dominant eigenvector of matrix A as the second notion of centrality. The third notion of centrality is what's called closeness, and this takes a distance point of view. Suppose you've got two nodes I and J, and there might be many paths connecting I and J. Let's say the distance between node I and J is the shortest one. We'll call this dij. Now later in lectures 9 and 13 for social and tech networks respectively, we'll look at how exactly can we compute, hopefully distributedly, these DIJs, search for the shortest path. That's not an easy job, but for today, let's assume somebody has already done that. So we can tabulate these DIJs for all the IJ node pairs. Then once we got this list of all the DIJs, we can do a few things. One is pick the largest one, and we call that the diameter of this graph. It is the maximum DIJ across all the IJ pairs. Okay. It's the largest, the smallest path lengths. Smallest for a given node pair and largest across all node pairs. We can also look at the average instead of the max of these DIJs. So we can sum up the DIJs. Okay. And then normalize. For example, we can normalize by the number of nodes, or the number of nodes minus 1 as is in the convention. Now this actually is in the opposite direction of closeness. Okay. That says the following. If I pick a node I here, fix I, and then look at all the other nodes J out there, okay, and there are n minus 1 of them, I look at the distance from me, node I, to all the others, the average. Then if this number is small, then I am more important, because I have a very short distance to all the other nodes. If this number is big, I am less important. So just to make the direction work out, let's take the reciprocal of this, n minus 1 over summation dij over all the ij pairs for a given fixed node I. This is what people call the centrality closeness centrality, denoted by C for this given node I. Now, if you have a high C sub I, it means that you have a very shortest distance to all the other nodes on average. Okay. Now, we didn't have to use the average, the simple mean. We can use other kind of means, for example, harmonic mean and so on. Now, this is not the end of it. There's yet another centrality measure that's often used. In fact, there's quite a couple of others as well, including another in the homework problem. But today, we'll stop with this fourth notion of centrality. We quantify it by the notion of betweenness. What does that mean? This goes back to Granovetter's 1973 experiment. It says if a node is sort of along the shortest path of many other node pairs, then it has some strategic importance. It's in the mix of the action. Okay. Any other node pairs, if they want to reach each other along a efficient path, then they have to pass through you. Okay. You're in between many node pairs. You're on many shortest path. And this is the idea of betweenness. How do we quantify this? Let's first denote by G sub st as the total number of shortest path between two nodes S and T. Okay. Then let's denote by nst sup I as the number of shortest path that node I sits on for the pair st. So clearly n sup I st is less than or equal to gst. Okay. Now this requires you to count for each pair st the number of shortest path. There might be only one, and node I might not be on it. Then you have 1 for gst and 0 for nist. So now we want to say, well, let me look at for each node pair st. They may have many shortest paths, so you have to normalize by gst. Okay. How many are you node I sitting on top of? Now this expression we then have to sum up across S and T. If we sum up across both S and T indices, we're actually double counting all the node pairs, which is fine if you want to stick to that convention, but most books stick to the following convention. You just order all the nodes, and therefore you sum across all the S and then all the destination T that's less than S in the ordering of the nodes. This will avoid double counting all node pairs. It's just a factor of 2 difference in the end. Now we call this a summation. The sum of the fraction of the shortest path that node I sits across all the other node pairs, betweenness for node I, bi for each given node I. So now we've got 4 notions. Degree, which we know is hardly a useful quantity in many instances. We have the eigenvector, the largest dominant eigenvector, the incidence matrix, adjacency matrix. We have the closeness centrality, ci for each node I, and the betweenness centrality, bi for each node I. So we've got 4 different metrics. Which one to use, again, depends on what you want to do. But first, let's illustrate these with a simple example. This is a network with just 8 nodes, okay? And we could compute the 4 different centrality measures for each of the 8 nodes. That would take too long time. Let's focus just on 2 nodes, nodes 1 and 2 here. If you just look at a graph, intuitively you say, well, node 1 got a degree of 3, node 2 got a degree of 3, but they shouldn't be equally important. In particular, this is like a dumbbell topology. The graph has a left side, a right side. Visually, I can see that this is an important link between the two, and node 1 is part of that link, whereas node 2 is not. So node 1 should be more important than node 2. So how do we quantify that notion? Clearly not by degree. Okay. Well, let's then look at eigenvector centrality. That means we have to compute matrix A here. What is matrix A? This is a graph that doesn't have directional links, so it will be a symmetric matrix. I'll just write down the first 2 rows here. Clearly, the first row says node 1 connects to 2, 3, and 4. That's it. So it's 0, 1, 1, 1, and then 0, 0, 0, 0. The second row, node 2, connects to nodes 1, 4, 5. So 1, 4, 4, 5, and 0, 0 everywhere else. Okay, you can fill out the rest, or you can take a look at the textbook. And now all we need to do is to compute the largest eigen value and the corresponding eigenvector. And we see the largest eigenvalue, which we are not using directly here, is 2.87, and x is the following vector. The first 2 components, which is what we're focusing right now, is 0.406 and 0.345, and dot, dot, dot. So you can see that node 1 is more important than node 2 now. Okay, at least they're not equally important anymore as in degree, but it is not a whole lot bigger than node 2's eigenvector centrality measure.